Are we ready?
Yeah.
All right, we're live.
Yeah, we are.
Okay, just making sure. Okay, so I was just talking to the people here, in live, in front of me. But we now actually started the live stream, so I'll introduce myself again. My name is David Acosta, and I am the beginner lectures tech lead for competitive programming, otherwise known as interview training. And the purpose of this is to help you solve the kinds of problems you would see at a job interview, where you have to know your data structures and algorithms. So this is the beginner lecture. So this is kind of just to start off, right? It's easy, get the hang of it, and know what types of data structures you need to use for certain problems. I guess I should say that my lectures happen every Tuesday at 3:30 to 4:45. Then the next day on Wednesday, hello. So Wednesday, tomorrow, and every Wednesday after, subsequent. We also have a follow-up lectures on what I teach, and Joseph's going to teach that. So he's going to go over what I taught the next day. And then Thursday at 3:30, Professor Geary is going to do the competitive programming lectures. So he's going to just lecture the team, everything you need to do. And he has his own schedule, so we have no idea what he teaches until the day he actually presents to us. So, and then on Friday, Lazaro here, who's the tech lead for competitive programming 2, he is going to go over what Geary talked over the day before. So every day, Tuesday to Friday, 3:30. On top of that, other events for DSC, we have the LinkedIn and resume workshop at 5 p.m. this Friday. So be sure to look out for that. Okay, yeah. For those of you here, sign the QR code there, or down here, if you're watching the live stream.
It's super short.
Yeah, just tell us you're here. We need to put that. Okay. So I'll leave you guys to do that. So I guess before we start, who has exposure to Python? Okay, a good amount of hands. Who has exposure to Java? So that's everyone. All right. So it's not exactly the same, but the concepts are still the same. It's shorter, it's more succinct, it's a little different, but you'll notice the patterns as we get the hang of it. So, but my lectures are going to be in Python, and Joseph's, he's going to do it in Java, so it's going to appeal to everyone. All right, so I presume everybody's signed in at this point, so I guess we could just start, right?
Yeah.
Okay, all right. Okay. So what we're mainly going to do, before I will sign up teaching, and this time I'm actually going to have you all interject and give me your opinions on how we should solve this problem, right? The problem we're going to solve today, well, one of them is going to be 2 sum, all right? So this is the way the problem goes. Given an array of integers nums and a target integer target, return indices of 2 numbers such that they add up to that target. And you may assume that each input has exactly 1 solution. And you may not use the same element twice, and you can return the answer in any order. Okay, so for example, you have nums, right? And the input is array nums 2, 7, 11, 15. And the target input is 9. So what you want to find are 2 numbers, and not just the numbers. You want to find the indices where they were found, the position, in a 0 index array. Return that pair of indices, right, as a list or an array, and return those, right? So here, the target is 9, and the output is 0, 1. Why is the output 0, 1?
2, so that's the index.
Yes, the index of?
2 and 7.
Yeah, the index of 2 and 7. So it's 0 index. So it goes 0, 1, 2, 3 in a size of 4. But it was these that added up to the target, 9. So this was index 0, 2. Index for 7 is 1. 2 plus 7 is 9. So we found the answer. All right. And yeah, I think we get the idea. Let's just get the idea of the constraints. The num's length can be 2 to 10 to the 4. The number could be from -10 to the 9 to 10 to the 9. The target could also be in that range. And there's only one answer. There's only one pair of indices here. Okay, yes.
Do you have duplicates?
Have what?
Duplicates.
No, you don't. You don't have duplicate numbers. That's the thing. It says it here. You cannot use the same element twice. Yeah. Actually, no. Yes, you can have duplicates. I'm sorry. You can't have duplicates. So here you have duplicates here, 3 and 3. Yeah. But no duplicate answers. I'm kidding. That won't happen. There's only going to be one answer, though. One pair. So, what do you think we should start? How do you think we should start, guys? Brute force?
Yeah.
Do you want to do brute force?
Yeah.
Well, actually, we could do brute force.
What if we
Okay.
sort it?
What if we sort it and then
Yeah. And now we have the numbers in order.
how do we keep track of the previous indices that were there? Well, someone said brute force. We could try that,
Yeah.
right?
Use hash map after sorting
We-
to keep the indices. You can keep a dictionary to note down the indices.
We could do that.
What's the data structure?
What is the data structure? Well, we're going to get to that.
Oh, okay.
Actually, I want to do what he did first. We're not going to. It's not going to be too long. I don't want to take too long with this. Range. Okay. Well, I'm going to do this part first. Okay. Do we know what's happening here in these two lines? Yeah. Well, you're actually kind of right. It is an advanced for loop, technically speaking. I mean, conceptually, we just look at this as a normal for loop in Python. But you're kind of right. This is I, number I, and it iterates through range n. And what that creates is an array or a list of numbers 0 all the way to n minus 1. Right? That's what range n does. And n is what?
The length of the array.
Yeah. Yes, it's the length of the list that we see right here. Okay. So obviously I is going to be 0. So what was the aspect of brute force that you wanted to put, Thomas?
I think that we should look at one number and then check every other number to see if that equals 9.
Okay. So how do we do that?
Make another for loop.
Okay. Make another for loop.
The first for loop marks the position of like the index that we're in, so like the first position, second position.
Right.
And the second for loop goes through the entire array X.
Okay.
It's a really good idea.
All right. So like this.
Yes.
All right. So can we modify this to be a little bit better?
Yes, you can have an if statement that filters out numbers that are greater than the target number. Maybe numbers that are also equal to the target
You
number.
can keep a range I plus 1,
Yeah.
comma.
Exactly. So you want to start at I plus 1. You want to start from here. Okay? Because we want to go after I.
Oh, true.
Yeah, and then check after that. Okay. Okay, so what do we do now? What do we check?
Oh, now we have now we actually do it. Now we do an if statement. If target equals num I plus nums and nums j.
Mm-hmm. If that what?
Maybe it should be the other way around. If not, then we break out of the loop and we go to the next value.
Why would we break out of the loop? Maybe
Go
we
to the next index.
maybe the next j is an answer.
If
If it fits the parameter, then we would try to return the output.
oh yeah.
Yeah.
Problem.
If it fits, see, we found target equals those two summed up.
Right. Yeah.
Done.
Exactly.
So return. So this is how you return. In Java, it will be new array list. But here, it's not as complicated. Just do that. See, just a list and two numbers, I and j. Okay. Do we really need anything more? No. Well, what is the? It doesn't say it. It doesn't say it. But if there is no answer, you have to return something, right? So outside of the the larger encompassing for loop, what do we put? I think we put -1 and -1. Oh, okay. Oh, well, the camera's being all.
You're still gonna look at it here. It's better quality.
Oh, really? Okay. So he's. But no, I'm gonna. No, this is in the way.
I tried to figure it out.
Okay.
You can move.
Okay.
You're fine. You're fine.
Oh, okay. All right. Just you got it. You got it, boss. Right?
Yeah.
You got it, boss. Okay. So he's setting up for the live stream, but you guys can see this perfectly fine. Okay. Oh, spam. All right. So if we run it, do you think it'll work? Oh, great. It worked. Wait. Oh, you put multiple test cases in here. Ah, I see. Yeah, so I'll also put multiple test cases. So for all these inputs, right? 9 from 2, 7, 11, 15, 0, 1. 6 from 3 to 4, 1, 2. Yeah, the index. And so on. It's accepted.
Let's go.
Excuse me. What is that part about return -1 -1? Like
Yeah,
sign?
basically, if there is no answer, just return this default -1. And think about it like this: -1 is outside of the index range in an array. There's 0 index, goes from 0 to n -1.
Right. Yeah.
So if I turn -1 -1, that's like saying, oh, there's nothing.
Oh, I see. Okay.
But yeah. Okay, so our runtime is 5,000 milliseconds. So that's basically 5 seconds. And that's faster than only 12% of Python 3 submissions. Memory, 14 megabytes. So that's less than 66% of Python submissions. All right, yeah.
Can you explain how test case, like what test cases are, how they work?
Oh, so go back to the problem here. So you have your input, right? And this input, this array, you see this array up here? That's this part. And this other part is this part. Those are different parameters. Do we see that? Okay. And so basically, this is one test case, right? And when we repeat it, it's another one. Usually, I just put one at a time. Like I don't put all of them together, but this is just for legibility. I mean, can I? No, I don't know how to increase the screen on the bottom screen. Do you know?
I actually don't know either.
Okay. I'm gonna actually, just to make it more legible, I am gonna do
Just click on test case.
right. I'm just gonna put 1. We'll do this. So basically, you can change your test case, right? So you can make it anything, and it'll still, the way that LeetCode tests it will still work. It'll still be working, right? So I can actually mix it up. Put that 11. That is 7. 15. 2. I'll run this code, new test case, and see. It's a different output, but that's because I changed the answer. I changed the test case, and LeetCode recognized that. So LeetCode knew that, I changed my test. It'll still work, and it will still test it fine. Now, I can also, I don't know, put this number, right? Will that return anything? What will that return? Solution either does not exist or it is not unique. Oh, it's an invalid. Invalid. I actually don't get that.
If it doesn't meet the constraints of the question
Let me
itself,
see.
then it's gonna say that.
But target is in the range. So. Oh right, one has to be okay. I didn't read that. Only one valid answer exists. Okay, so actually, this part here is kind of useless. But the thing is that Python, or really any programming language, outside of an if statement, you do need a return, right? Especially if you specify. Well, I mean, okay, yeah.
Also, what I was just getting at is that like sometimes you might work in certain test cases, and then you like realize that your code doesn't actually work in all test cases.
Yes.
Yeah, that sucks.
Yeah. So you might think you solved the problem. Actually,
It's kind of like me.
Yeah,
I thought
yeah.
that was gonna work. That was the worst idea I've ever had.
oh, so you're putting it back to this?
Yeah.
See?
Like, it was so blurry. It honestly looked horrible.
Well, we have no choice but to put it on the projector.
Because it's on his computer.
Yeah. I don't know because that one's streaming and that one's doing that.
We all moving around.
Anyway, back to what I was saying, right? So your code might work for one test case and not work for another. So you might put run code and it works, but then you put submit and you fail. And then what they give you is the test case where it failed, right? They give you that first failed test case, and you kind of have to like work it out. So then after you find that it failed, it's on you to kind of figure out why did it fail. I'm gonna move on. Actually, I'm going to actually.
Quick question.
Okay, yeah.
Can you explain the time complexity of this?
Right. Okay, so we have our n. Isn't that great? Okay, so what do we know about big O notation?
It's how long it takes the computer to sort through
Mm,
an array. Like there's different ways of doing it.
it's a little reductive because you're talking about just arrays. It's not just arrays. Yeah.
All computers are different, and they're all going to predict different times that a program or an algorithm can run. So big O notation is just to, or the way I see it, is just a way to measure it.
It's really not. It's really not so much technical as it is theoretical. So it's really mathematical. I mean, yeah, you're right. Different computers take different. Each process takes different time in each computer because of like maybe it's a faster processor, and all that stuff. So let's say going through an array. How long should that take?
Depends on length of the array.
The length of the array, right? So
Depends upon the length of the array.
so the array, in this case, is length n, right? So it's variably length n. So we say that in big O time complexity, it takes big O of n to go through an array. Are we good on that?
Yeah. Depending on the algorithm. Yeah, exactly.
I mean, sure. I mean,
Linearly search it, then that's all then.
Okay, can you give me any example which doesn't
well, right.
provide big often in terms of iteration of an array?
Sorry. Like,
So you said that it depends on the algorithm, right?
yeah. No, yeah, but if you do want to look at every single index, then it is O then. But I'm saying that some algorithms can vary, so it's not always O then.
Or can you name one?
Like binary search.
We're gonna go into that. I really. Yeah. Exactly. Okay.
Is the time complexity is the cost of the section in your code that does most of the amount of work. So you can do a linear search, but after the linear search, if you're doing n squared, your algorithm is n squared. So although your algorithm has O of n, the n squared is larger than O of n. So you say your big O time complexity is O of n squared.
Okay. All right. So I'm just kind of making it easier. All right.
So.
So do you? Okay. No. Go ahead. Go ahead.
Yeah, so in this case, the outer for loop would traverse the entire array in O of n because it look at every single element in the array once, and there's n elements, so it's O of n.
Yeah. Exactly. So what about this for loop that's inside?
That's going to cause that outer array that is O of n to happen n times.
Right. Well, it's really just I plus 1.
Add another and ask them what do we do.
Huh?
Add another and ask them what do we do.
Okay. Let's say I'll put it after the if statement. For k in range. It doesn't matter. Blah. All right. How many times is blah going to get printed? Yeah.
So every time the if statement doesn't execute,
The what?
doesn't execute, the for loop gonna.
No. This is after the if statement.
So in that case, it would execute. Okay. Yeah.
Let's ask for time complexity. This is kind of.
What's the time complexity of having 3 nested for loops? Yeah.
Big O of n cubed.
Why is it big O of n cubed?
Okay, because
If you want, you can draw on the board. If it helps.
I don't know. Like you said, we have 3 for loops, so I don't know. This stuff is hard to explain. That's all. It's just.
Okay. So I'm gonna erase this for loop, just so we can make it simpler. Okay. So the inner for loop is O of n. So the inner for loop is an O of n operation, algorithm happening O of n times. So it's n happening n times. So all in all, the whole the whole thing is big O of n times big O of n, right? That's big O of n times n so it's big O of n squared. All right, so I guess it's really conceptual. You know what? I'm gonna be I'm gonna go on Desmos just to show the graphing calculator. Okay, so n y equals n. Okay, y equals n squared. All right, so I'm gonna do this. Okay, so let's assume that n is this dimension, and that's the size of your problem, and y is the time taken to solve it. Which one grows faster?
Depends on how big the data structure is.
Right, so that's the variable here on the x-axis, or the n-axis, I'm calling it.
Yeah.
So let's say the red solution is a solution that takes O of n time, and the blue solution is O of n squared. So look how fast the time taken to solve it grows with the adding size of the problem in O of n squared versus O of n. Do you see what I'm trying to conceptually portray? Okay, yeah.
The thing is that when it comes to like the size of the array, it's slightly more computationally efficient. Like if you zoom in, the linear one is a little bit faster than the.
Okay, but let's say our n is actually.
If it's like 10 trillion, then yeah, of course.
Okay,
n
so
squared.
num's length could be 10,000.
Oh, then yeah, n squared.
So,
for sure.
and most of your tests, hey Demba, most of your tests are going to be on the bigger side.
Right.
Right.
Okay, then yes.
Can you go back to that? Can you zoom in?
About to go home. Yeah. You mean this
Yeah.
part?
So notice how for what you said, how in the beginning it might be, you said it might be more efficient.
Yeah, but
Yeah.
it's like one value.
Yeah, it's just one.
It's actually a fraction of it. At 1, they're exactly the same, so there is no edge. But it has an edge when it's less than 1. In that case,
Okay.
it's impossible because you can't have an array.
Right.
Yeah.
Path.
Yeah.
Okay, yeah.
So
I thought it was bigger.
basically, what is a better solution? The red solution or the blue solution? Red, right. The red solution is better because as the problem grows here, the time taken doesn't grow as fast as for the blue one. So is there a better solution than this? Where we can, where the time taken doesn't grow so much as fast as, What could we do?
If we iterate through the array once, maybe it would just be O of n.
Okay. If we did it once, but then how do we find the values? What do we do to, say we're at one value, how do we find preceding values to get to the target? What do we do?
We can save the values.
We could save the values.
Other way.
So we cache it, right?
Yes.
Yes. Yeah, we get what Clement says, caching it. So we cache the values that we've already seen. Okay. Do we know what we're talking about? Any hints on what we're gonna do next? Anybody?
We're
Why-
gonna use dictionary.
Huh?
We're gonna use dictionary
Yes.
Why is that helpful? Why do we want to cache it?
because we want to solve it below n.
Yeah, but how can that caching help us? Or how can that adding to this data structure?
So okay, we can just for each element in array, we're gonna subtract with the target, and we're gonna find it in the dictionary, so that we can find the target. We can other positions. We can return them. Yeah.
Yeah, right.
Because when you cache it, it's O of 1, so
Yeah.
it's more efficient
Right.
than going through an entire array.
Yeah, so that
Yeah.
comes with the data structure, but like he
Yeah.
said, like the advantage of adding it to this O of 1 data structure, a hash map, is that if you compute the difference, since your data structure is not O of 1, all you have to check is that difference if you've seen it before. If you've seen that difference before, then you know you can add these two numbers up to get your target.
All right. So
That makes
Like-
sense to everyone, right?
you all get
If
it.
you didn't, we can do an example with David if you want.
Um,
Can
You
you explain
guys-
like O of 1 maybe? Too?
O of 1
Yeah.
to cache it.
Yeah, just O of 1 in general. Like why?
Okay, O of 1 is an operation that happens not instantaneously, but let's say you have a problem size n, right? But you're doing an operation print hello. Does this operation print hello get affected by the size of the problem, the size of the nums array? No, it doesn't, right? So the size of the problem doesn't affect how long that operation takes, which is why we say this operation is big O of 1. It basically means it runs in constant time.
Actually, so okay.
Yeah.
So every operation other than the iteration is big of 1. The print statement internally travels the entire string, so we can't say that.
Oh, okay, yeah. Of course, it depends on the size of the string. Yes, he's right. But the size of the problem is pertaining to nums.
Yeah.
This has nothing to do. Yeah, exactly. So this will happen at its own time, irrespective of whatever. So basically, this could take, I don't know, 100 milliseconds. That is still big O of 1, right? Because it is constant, it will never change. So we may as well say it's O of 1. Okay? So that, I'm going to just comment that out. All right, so we can get on. All right, so now, Thomas, you said to cache it, right?
Mhm.
So we're going to use a hash map, or a dictionary. That's how we use it. I'm going to call it without the I. All right. So in Java, well, do you think I need to do this, the Java version? Maybe just to show.
Yeah, a lot of people here program Java. Why not?
So, do it like this. So in Java, you would make it like this. You would import it, obviously, right? We're going to make it of an integer. I'm going to say map. No, I'll call it the same thing, dictionary. So here's the Java version of doing basically what the line above says. It's much shorter, right? It's a lot shorter.
Terrible.
Yeah, I know. But oddly enough, Even in typing it's slow, but in compilation it's actually faster. Yeah. So, because Java is a compiled statically typed language, Python uses an interpreter, which means you have to infer type, and that takes time. So I'm not going to go too much into that, but the point is that it's easier to type in Java and Python, so it's easier to kind of go through it in Python, which is why I chose it. But you all could follow along with that, right? You all know what that's doing?
Just creating a dictionary.
Yeah. And a dictionary has what?
Key value pair.
It has a key value pair. So you can get a key value, right? You put get key, and it'll return you the value. Does that make sense?
Can you explain dictionaries a little bit more than that?
Okay. So I could have, I don't know, A1, B2, C3. Okay. So let's say I set it up like this, right? So what are the key value pairs here? But what are the keys? A, B, and C are, strings. Those are the keys. And each key is mapped to a value, which is A is mapped to 1, 2 is mapped to B, 3 is mapped to C, right? So if I do, right, what does that return?
1.
Right, so that returns 1. You could also do this. And what will that return? 1 as well. It's also something a little fun, right? What do you think this does?
It sets the value to 0.
No, it does not set the value to 0. What this does is that it gets it.
Oh.
It gets the key. And if it's not already in there, it will by default return the value I put in there, in the second parameter. It's a get or default to this value. Okay? So this will return 1 because A is a key in the dictionary, so it'll work. Do you think that was good, Thomas? All right. So how do we start out, right? What are we going to do? What are we going to do to start out? Huh?
You delete it.
Think I should keep it there?
No, you gotta delete the dictionary.
Well, I don't want it to stay like this. I'll do it like that.
Yeah.
No. Just that part. Just the whole line. Okay. So I commented out the. Okay. No questions? Okay. All right. So how do we start out?
Maybe we can create a brand new dictionary and add the values. to
Why?
it. So like the key could be the index, and the value would be like the value at that index.
That is exactly, yeah. I mean, that's the dictionary we're going to use. It's going to be the value at that index, and then the key is going to be the value of the index. And the index is going to be the value itself, mapped to that key.
Right.
Do we get why? Do you understand why we're doing that? Okay.
Wait, so the key is the index?
No, the value is the index, and the
Yeah,
I know because it's
The number is the key.
okay.
The
The
index
number,
is
right? Thank you, Lazaro. The number at that index is the key, and its index is the value.
Do an example.
Huh?
Do an example.
Do an example. Okay.
That's probably easier to draw than this.
Or you
Yeah.
can do it for-
Do it on the board. Are you gonna? You have to turn the lights on.
Okay.
Yeah, you can see it. I think it's not that dark.
Not that dark in here? No, but I think for the
Oh, for the camera.
for the camera. So do I go around? Or go-
Oh, I thought you could do it right here.
Oh, okay. I'll do it here. Oh, move the camera. Okay. So, right. So there's an example. We're going to use this one. We're going to use example 1, right? So I'm going to say that nums 0 Yeah.
Yeah, question. So how can we handle duplicates again?
What?
How can we handle duplicates?
Oh, that's a good point. So,
What if the solution only is by duplicates?
well, see, here's the thing, right? It doesn't matter. It doesn't matter.
Sorry?
It doesn't matter.
It matters.
No.
How come?
So it doesn't matter because the first time you see, like, say, a 3, and then the first 3 you find, you know, okay, so let's say you put in a 3 and you see a 3 again, right?
But we're gonna return the indexes the second, third, right? So we have to.
Okay, so here's the thing. There's only one solution, right?
Yeah.
Right? So it only matters if it's 3 is part of the solution, whether even if you see it twice, like. Okay, so I'm gonna do like this. Okay, and then I overwrite it.
Okay. Let's. Okay. Okay. Fine.
You know.
Make the target 6. I think that's what he's trying to say.
Yeah, that's one. Then we don't have a solution using the dictionary, I guess.
We do. No, we do. So I'm going to put this in the dictionary. So 3 is going to be there.
Okay, and the value would be 0.
Yeah, it will be 0,
Yeah,
right?
and
And then I go to the next one,
Yeah, the value
right?
would be 1.
Yeah, and then, so here's the thing. I'm going to put it right here. So I'm going to say, get a difference, right? And it's going to be the target minus the current number we're at,
Okay.
okay? And if that is in the dictionary, then what we want to do is return, what is it? It doesn't matter the order, but I think I'll just put this first. No, actually, no. This does come first. And I. Okay.
So wait.
All right. Yeah, I know the confusion. Huh?
How are we creating the dictionary?
We okay.
array?
Yeah. I think this is 2 verbose. I think we're just 2 verbose. I'm gonna remove a bit. Sorry. Just so that we have it simple. Okay. You're asking how did we create the dictionary? We created.
No, I see it there, but we need to put the values in it first.
Right. We do. So, if
Oh, okay, so we haven't done that yet.
we haven't done that yet. So if that difference is not in there, right? So we didn't find another number that pairs up with the current number we're at right now. Here's what we do. We put it in there.
Oh, okay.
Nums I, like what we did right now. I. Okay. Let's run this. So, you know, it works with one test case, but it may not work with all of them. So I'm going to risk it all and submit and maybe ruin my rate. There we go. So this, thank you. So the runtime here was 89 milliseconds versus the 5,000 milliseconds.
Oh, wow.
Yeah, it had a lot to do with that whole curve thing that I showed you earlier on Desmos. Yeah, so depending on the type of solution you're going for, it might affect the efficiency of that solution. Okay, do we get that? All right, yeah.
I just have a question. So the difference that we're doing here is that instead of iterating through 2 arrays at the same time, we're just doing it once.
Yes, we're only iterating once. So instead of like iterating through it n times, doing n times, we're doing n, and that's it. We iterate once. That's all we need.
That's awesome.
Yeah. Any questions about this? Yeah.
Yeah, so the in operator we are using the diff gonna iterate over all keys in the dict, right? No?
No, the diff is one number.
Yeah, dict, sorry, I'm saying dict. DCD.
Yeah, dict is going
The
to.
in operator
Yeah, yeah.
will try to iterate over the keys in the DCD
Mm,
for the diff value. No?
No. Okay, so we're iterating through the list of numbers, right? Nums list. We're going to iterate through it, and we're going to add numbers, and we're going to end their index, right? And if at the next number, right, the target 6 minus its current number, we find that it's equal to 3, and that key is present in the dictionary, which it is, and finding it, searching a key in a dictionary is O of 1. It's constant.
So we
I-
can also write it as dict of diff, right? That's all right?
Dict of, yeah, exactly. Yeah. Dict.
But, okay. We might get key error if its value is not there.
But this is the thing. If I'm checking,
Yeah.
this test is going to be constant, right? So if it is in there, return it. If not, then after the if statement, you set it.
Okay. Yeah. Fine.
Yeah.
I think it would make more sense if you just like ran by like what the dictionary is at each index, and then be like, here's what the difference is, and here's why it ends here, kind of thing.
Okay. So this example,
Yeah, it's fine.
You might have to look at
I might have to move.
Yeah.
Just use like a regular example. The test case here is fine.
Okay. So I'm gonna do the test case then. So Lazaro's gonna move the camera around. Okay.
You could have gone around.
Okay. Well, shut up. Okay. So we're here, right? Dict equals is empty, right? I'm gonna iterate through it. I'm here. So I have to check that 2 is in dict. So diff to start is going to be, oh, I didn't set target, it's 9. So diff is going to be 9 minus 2, 7, right? So is 7 a key in this dict?
No.
No. So now what we're going to do, we're going to put the value we're at as a key, nums I, or num0, and then we're going to put the index. Right? Okay. Then we go to the next one. We move I up. And then diff is 9 minus 7. That's 2. Is 2 a key? Yeah, it's a key. Exactly. So now we're going to return dict of diff. And diff is just 2. And 2, this is going to be 0. And then we're going to return I. And I is just 1. And, well, you don't see it, but that is the answer. The answer is this pair of indices, 0, 1, which these two add up to 9, which is the target. Okay? Does that clear everything up? That's great. All right. So I didn't think we'd spend this much time on this problem. Like I wanted to go over threesome. I don't think we.
Leave it for homework event.
Okay.
Or you can introduce it.
I wanted to introduce the other. Yeah.
What's the trade-off between this solution and the other one?
So there is a trade-off. There's a pros and cons. This solution is great for time complexity, of course, but there is a cost. Well, can any of you guys guess what the cost is? Yes, the space. Does anybody see why the space would be sacrificed?
You have to store all that.
Right. You have to make a store of all these keys and then indexes.
Do we have a solution without space complexity then?
Well, that was the other one. The one we just did was O of 1 space. We didn't use any extra variables that were variably long, right? So, do we get that? Do you have any questions about that? We're gonna do any questions on the chat? No? Okay.
I have a follow-up.
Oh, really?
Yeah, just for, he's looking into threesome now, but just for homework, or you guys want to think about it, can we have constant space complexity and have a time complexity that's better than n squared
For this problem.
for two sum?
Well, I don't know about this particular one because this is concerning indices. Were you able to do it?
The one?
Because this is you have to preserve the indexes.
Yeah, I know.
Okay. If it was a different.
Yeah, if it was the other one.
Okay. Right. Yeah.
What's the one more? Sorry.
Yes. Kind of prove if you can get it better than n squared, with constant space.
All right. So I am going to go over threesome, but I may not have time for threesome. So I'll do a different iteration of this problem. Let me see. Okay, yeah. So now this is two sum, but now the numbers are sorted. So numbers are sorted, so that kind of improved things a little bit. So that might decrease the need for something.
You don't have to save anything, right?
You don't have to what?
You just check accurate now. Never mind. I don't know what I was gonna say.
So we needed to do something here, right? To make it more efficient. So now we're here and the constraints are different. Now the numbers are sorted. Does that decrease the need for something? And if so, what is it?
Should you not? I guess you don't need the dictionary anymore. You can just sort it in a single. Right, it's already sorted in a single array.
Right. You don't need the dictionary anymore. So what's the space? Well, what could be the space? Is it possible the space could be constant?
Yeah, if you don't have like another array or anything, another data structure.
So you don't need one for this one. In fact, all you need are two variables, and that's it. So I'm gonna make L left. I'm gonna make left. Should I put it in like comma, or is that gonna confuse them?
Might confuse them.
Okay, so I put them in different lines. Okay, so left, I'm going to set it to the beginning. Now right is going to be equal to length of numbers minus 1. Any ideas why I'm doing that before I go to the next line?
That's the index of the first element and the last element, yeah?
And why am I doing that?
So you're setting them as far away as possible until they meet in the middle and have the difference that you're looking for?
Yes. So I'm going to actually make them meet in the middle, right? This is known as a two-pointer solution, right? So you have 2 pointers and you want to change them in a way such that, yeah, they meet halfway. So they might meet right in the middle, or they might meet like, over here. So what will that look like? And obviously, it has to be different numbers, different indices. So is this right? Is that right?
Now,
Why isn't it right?
so because when left and right is same, we can't. There might be a solution.
Yeah.
We can't change two same indexes.
Yeah. So basically, left and right will be the same index, and we don't want that. We want them to be different.
Yeah.
So we want them to be less than. Okay. All right. So we're going to, what are we going to do? We could say we have an addition, right? Equal to nums left plus right. No, sorry. Okay, numbers. Okay. All right. So this was a hint that I gave. What do we do after this? We have an addition, numbers left, numbers right.
I'm guessing if addition is not equal to the target number, then we increase left and we decrease right.
So we move them at the same time? Who agrees with that? Who agrees? Wait, who? Okay,
So
yeah.
if the answer is less than the target, then you increment the left, and if it's more, then you decrement the right.
Okay, Decker, exactly. So, well, let's do if the addition is equal to the target, right? Get this out of the way. Drag it. Right? Then you will return, right? Left and right. Everyone agree?
Yes.
L if it was less than, you said increment the left one, right?
Yes.
Plus equal 1. And the default is just that it's greater than, right? And you said decrement the right. We get this so far?
Yes.
Okay. And by default, I'm just going to return -1 and then -1. It doesn't matter. I could also return an empty list. I think, yeah, it says you will have exactly one solution. Okay. All right. So let's run this. Okay. Does not work. Okay, to 1 and 2. Therefore, to 1, 2. This is not 0 indexed. They don't want it 0 indexed. Yeah, so it's 1 indexed, which is no problem. This is a simple fix. I mean, if 0, 1 is our solution, it's 1, 2, what can we do to our return statement? Yeah, exactly. We just plus 1 on each.
Wait, but why?
Oh, because that's added by 1.
Oh.
Added by 1 as an integer.
Yeah. So it's going to work for this one. It's going to work for this test case. Does it work for all of them? If we find the mistake, it's going to give us a test case, and we just put it in here. All right, it does work. Let's go. All right. So I thought it was logic. It was completely just not reading the problem.
Yeah.
Okay, any questions? Yeah.
So do we have a solution where the array is not sorted and the space complexity is big of 1?
I really don't think so. I don't know.
So what?
Maybe. Maybe. Yeah, like if it's it's not sorted and the time complexity
Space?
is the space complexity is O of 1 and the time complexity is O of n.
Yeah, and the array is not sorted.
Yeah, are you referring to the question I asked?
Yeah, that's it.
Yeah, then yeah, you can't do it. Because
Yeah.
you don't know, since it's not sorted, you can't do any operation on the remaining numbers. So you can't do, for example, binary search or whatever, what David did right here. So you would have to look through it, so you do need that n squared. So the answer was no. Yeah.
Okay. So what's the time complexity? N? And why is that?
Because we're,
Because
Yeah.
you just need to iterate over the array once.
Yeah, exactly. So you're going to iterate linearly through the array. I mean, it's going to be like one's moving this way, one's moving that way. But that's no different from doing this. You're going through pretty much all the elements. I mean, maybe. It might be that they're all, you one's here, one's here. But the worst, big O is always about the worst case scenario. What's the longest amount of time it could run? So it's O of n. They might actually meet up. And if they meet up, that means you went through all the elements, right? Exactly. Do we see that? No question on that. So both these questions are actually going to be very helpful when you want to solve this problem. Okay, let me go over here. 3 sum. So this one's a little different. Given an integer array nums, return all triplets nums I, nums j, nums k, such that none of those integers equal each other and all those numbers add up to 0. Okay? And what you're going to return is all the possible answers. Yeah. So this is a little complicated, huh? So here you have nums equals -1, 0, 1, 2, -1, -4. And your output is this one triplet, -1, -1, and 2, -1, 0, and 1. Oh, and goodbye. Thank you.
Bye. See you tomorrow.
Yep. So, and we're also adding the actual values, the numbers, and not just the indices. So we're not worried about indices. So these are all the possible triplets in this nums array that add up to 0. Do we get it so far?
Yeah.
Okay. And okay. So we get what the problem's asking us. Okay. Okay, good. So, what do we need to do?
Well, we could brute force this one. That's always an option.
Right.
What I'm thinking of is we store the
Mm-hmm.
and we look through it. Now it's not the most optimal solution, but that's what I'm thinking of at this moment.
Hmm. Well, this is the hint that I am giving you guys. You need to incorporate this and this.
Oh.
All right. And another thing, this array is unsorted, the way they give it to you.
We can sort it. Right?
Why? So why?
You want to use two sum two solution at all, you need to sort it.
So this, yeah. So this solution is giving you a sorted list, right? So you have to sort the list in order to use this sort of paradigm. Yeah.
Yeah, so the solution would be first caching the indexes. Okay.
Uh-huh.
Now,
I mean,
Yeah, there's something else to notice. This,
Oh, yeah.
it's not.
it's not indices.
for
It's not asking you for indices.
Yeah.
It's number values, triplets of number values of the array.
Yeah.
So in that sense, it does make it easier where we don't need that hash map storing the original indices. So we can just straight up sort it without worrying about messing up the index.
Yeah.
Okay. We get that?
Yeah.
So in order to use the second one, this is where we start off. So we're not going to go over sorting algorithms in our beginner lectures. We did that last semester, but we're doing problems. And I mean, you just got to know that really sorting algorithms take O of n log n. Some of them take O of n. There's one which is radix sort, which is just bucket sorting, or sorting by.
Average, no?
Really? Bucket sorting is not average.
Like average open.
Yes, yes, yes. I'm saying that. Yeah.
Oh, okay.
Yeah, yeah. The only O of n linear sorting algorithm is radix sort, or it's kind of bucket sort.
Wait,
Actually,
big O.
big O of n.
is n.
Yeah, radix. Yeah, it's linear. Yes.
But it only works for certain.
For certain
it
test
doesn't
case.
work for everything.
Yeah, so
It's
worst
like
case is n.
numbers and strings or something like that.
So what's worst case n squared?
No, the worst case is O of n, but
Yeah.
it is only O of n worst case for certain like integers or something like that.
Certain integers.
Yeah,
Well, I
I'm not
mean-
sure, but there is like a.
But
thing
that
with-
case is no longer O of n. If it's worst case, then you can't take special cases.
So here's
Yeah,
the.
I don't think you can't possibly have like you can't compare everything in O of n. It has to be log of n. That's the lower bound. But it does do it in O of n for certain things.
You know about logarithms, right? Okay. So I guess I don't think we're gonna go over the problem because it's kind of long.
Is it amortized? Is that what?
Okay. So basically,
I'll search up fine.
okay. We could. I mean, we could talk about it. We're not gonna do the threesome. That's gonna be probably homework.
Yeah.
We could push it out. You know. Oh.
Look, this guy knows.
He knows how to solve the problem, right? But hold on. Can you explain to us how radix sort works?
Not even that. This is a
Radix
bucket
sort?
sort guy.
Okay, you guys.
Radix sort.
So
He
radix
loves
sort.
bucket sort.
Oh, buckets for a radix sort.
They're not saying?
No.
No? Really?
Not this one.
Whoa.
You use bucket sort when implementing.
You use bucket with radix?
No, it's like you sort of use that concept here.
Yeah, use the concept.
Alright, is it all of n? Big O?
So it's O of n times m.
Want to turn on the light?
N times m.
Oh, I can type it. You want me to type it? Or whatever. So radix sort is, let's say you have numbers like this, 123, 45, and 7, 2, 3,
Can you turn on the light?
and, no.
No, for the camera.
Oh,
Oh, but yeah.
I wanna see.
alright guys, so you have the numbers like this, and then let's do another number, 421, right? This is in your array. Radix sort basically takes precedence over the first element, right? Or is it the last one? Sorry?
I'm not sure. It has to be.
No, I think it's the smallest one. And then
it's
it
the
goes
least
up.
significant.
Yeah.
Exactly, yeah, the least significant, yeah, okay. So you look at the least significant one, and it's one here, yeah. The reason you don't do the first one is because 4 right here is in the hundreds, but over here, this 4 is in the tens. So it wouldn't make sense to do it in the beginning. But right here, the last one of each one is in the ones place, right? So you can compare them all. You can say, okay, well, which one's bigger, right? So for this one, which one's smaller, right? So for this one, 421 would be first because it has a 1, it's the smallest element. The second smallest element, well, we'd have to choose between one or these, right? And at this point, they're both basically the same. So you can put whichever one, doesn't matter. So you do, let's say 123. Or actually,
Well, can you put the
it'll be better. 'Cause
Can you
get
put the
to see
buckets?
The concept better. Huh?
Can you put like the buckets of like the 0, 1, 2, where it's placed in the stacks? I'm sorry. Thank you.
So we put this one right here, and then this one we put it. Let's do it'll be a better example. We do this one first. 700 and 23, and then 123 since they're both the same, right? And then for this one, we put this 45, and this one kind of just stays empty. Is that it?
No. I think it's
I don't think it's the
no. You have to do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And then the least significant digit, right? You put it where it belongs. So if it ends in 1, you put it in 1, and if it ends in 3, you put it in 3, and then it's a stack, right? And then when you're supposed to, you fill up the buckets, you fill up the stacks, and then you pop it out in reverse order on the array, and then that's pretty much it. No, I'm sorry. Continue.
Right, maybe we should just continue with the
Mhm.
two sum.
Okay, you wanna continue with 3 sum?
Okay, so let's take a look at something.
Let's take this concept. I just forgot how to put it. Is it in a bucket or?
Your time complexity is like it's W times N, where W is the key length and N is the number of keys.
Well, we could say W
Yeah.
could be the largest integer
if
value.
they're all the same, then
Yeah,
it's
exactly.
constant.
So it's constant.
So worst case,
Yeah.
it would be the
Yeah.
worst.
It's Google Radix, RADIX sort.
It's a really cool sorting algorithm.
Yeah, but most sorting algorithms are going to be comparison sorts, especially the ones that Python and C++ has like by their libraries. So it's going to be n log n.
I'm a bubble sort kind of guy.
You like bubble sort? Well, you also like flunking tests.
I have no idea.
You like flunking tests and doing naive solutions.
I'm a web developer.
You're a web developer? Is Center a div?
Yeah.
Joshua Fluke?
Yes.
Just fine technology.
So let's take a look at these. These are like the basic time complexities. There's more than just this. But let's consider this n, the size of the problem, and this y, the time taken to solve it. Oh, okay. Do we get this? Actually, let me put another one. Y equals, okay. All right, so which is the one that grows the slowest? Log, right? So it's like, it's really, really slow. So everything's growing fast and it's kind of just going, It's taking its time. Right. It's kind of what I was saying before. And then the red one is x or n, and then the blue one is n log n. So which one's better, n log n or n?
And log
Well, I'm gonna zoom out. What about now?
in. Yeah.
And
And log in.
No, n log n's the blue one.
Wait. I thought if it was going up faster, that's better.
No, when it goes up fast. This is my fault. I wasn't being clear. If it goes up faster, that means it's a terrible solution. But relatively speaking, because that means that as the problem grows, the time taken grows faster than other ones. So it's going to be a lot slower than other more efficient problems.
Oh, I get it now.
Yeah. All right. Yeah. Okay.
And
Okay.
I think the good
Yeah.
Yeah, an array that's like a million in it.
Yeah, you have a lot of users, a lot of clients, right? And you gotta like make that work into that app. So you want the efficient solution as possible, or it's gonna be slow. And when it's slow, users get really mad, and credibility goes out the window. So it's important to understand things like this, right? This is also the basis of like competitive programming, or just like solving problems in general. Okay, so another interesting thing, I'm going to keep the green one. Actually, I'm going to do this, right? I'm going to keep these two. Okay, so we know that the blue one's better, which is n log n is better than n squared, right? Okay, let's say for the blue one, I add a n squared to it. Okay, now what?
No, it's n squared.
Yeah. Why is it n squared?
Because in time complexity, you have to take the biggest
Right.
operation number or whatever.
So the biggest term in your equation, or so let's say that you do a sorting or whatever, and then after the sorting, sequentially you do a n squared thing like a nested for loop or something. I don't know. So the actual time complexity overall will be the blue one and the green one have the same time complexity, right?
Theoretically.
Yeah, no, they do. They have the same worst time complexity to solve the problem. So the largest term always overtakes all the smaller ones. I mean, I could add a plus n plus log of n, whatever, it doesn't matter. It's still the same because of the largest term. I mean, think about it like this. If I put, what is it? It's a coefficient, right? See? Let me just.
So we get it.
Yeah.
All right, you guys understand. But see, that's the thing. It's always the largest term, and it doesn't matter what coefficient is there. 3, 1, 100. It's the same time complexity. Your time complexity of your problem is always bounded by the operation, the algorithm that takes the longest. So always keep that in mind when you're solving your problem. So let's say you have an O of n thing of one for loop. But before that, you sort the number of, the array. Well, sure, you have an O of n solution after the sorting, but the sorting took much longer than that. So basically, your solution, the time it took to solve it, is bounded by that sorting operation. Do you see what I mean? Does that make sense?
Yes.
Okay. So actually, let's say this wasn't sorted. And you just had to return numbers, right, instead of indexes. Well, then you did have to sort it. So you may have a while loop that's O of n, right? But sorting it makes it take longer. So the time complexity is going to be bounded to how fast the sorting takes, if you put it in there. Do we get that so far? Any questions on that? Yeah.
So if we had two for loops, that would be like n squared.
Yeah.
Okay.
Well, it depends on what the for loops have.
That's what I meant to say.
Yeah, if you had two nested for loops, and they each iterate through the array, then yeah, it's n squared.
All right, perfect. Thank you.
Yeah. But if one for loop, if one loop inside the nested loop, if the nested loop is log, right, and the other one is n, then it's multiplied. It's n log n, right?
What
Yeah.
does log even mean in the concept of time complexity?
So
Kinda shared it.
it kind of, yeah. I'm gonna.
You gotta take calculus.
Yeah. Let me see. Okay. So if it's size 4, it's 2. If it's size 16, it's 4. So basically, log just means like the reverse, getting the exponent, right? Yeah. Okay. Demba.
Do you want to suggest maybe like if we explain it using dynamic check, like it makes it very clear?
We're gonna go over that in another lecture. Yeah, we are gonna go over that though. Yeah, binary search goes over this, and that is a log of n solution, right? So it's a solution where you're not required to go through the whole array, like at all. It'll only take log of n time. The base being 2 because it's binary. You're cutting it in half, which we will go over another time because we are out of time. Yeah, so thank you for coming, guys. Make sure to come out to tomorrow's lecture if you can. Thursday also we have Gary's lecture, and Friday Lastro's going to go over it. And yeah, our LinkedIn lecture is on Friday at 5.